In this video, we're going to discuss quantum numbers of orbitals, which is really just a way of telling you which energy level you are in. Quantum numbers just mean discrete. Remember, you can only have set amounts, and so you can only have specifically shaped orbitals. All these values tell us what that orbital is, but it's important because it helps explain a lot of what we see with the periodic table. To start, N. N values are anywhere from 1 and up. N just tells us about the number of nodes. Specifically, my nodes equals n minus 1. They decided not to use 0 as the first, so you always have to subtract 1 from it. When I think about hydrogen, hydrogen is the simplest atom. It has just one electron around it. That electron doesn't have to worry about any other electrons, so when I have hydrogen, it has an electron that is hanging out at the lowest energy. And sure, there are other orbitals, because we see transitions when we do obtain the line spectrum. But that electron is just hanging out at the bottom. Well, what is that orbital? What is its shape? It is the simplest shape. It is just a sphere. We call it the 1s orbital. So where does that come from? What does it mean to be 1s? Well, s orbital was spherical in shape. Remember, our spheres are s, our 2 lobes are p, our 4 lobes are d orbitals. So that hydrogen has an s orbital. We call it the 1. That 1 is the n value. It just tells us, hey, it's an s orbital and no nodes. Because remember, my nodes are n minus 1. And so it's an s with no nodes. Well, how can an s have a node? We talked a little bit about nodes for p's. There's a plane that cuts. Basically, it splits the s in half, and so that's how you get a p. A d, you did it twice. You had a plane, one up and down, one left and right, and split your circle into 4. Well, you absolutely can have 2 s orbitals. But this means I have to have a node. This would be 1 node and s shape. What is a 2s orbital for your electron? It's a sphere that has a node. Well, if I put a planar node in, I look like a p orbital. So I can't put in a plane, but there's a cheat. When we think about a standing wave, and we had our original, we could add a node in the middle, and that's where we got our p orbital from. Effectively, you said, hey, this whole section can't have any intensity there. It has to be 0. Well, spinning this into 3D gave us 2 options. One was to create the p orbital, where these were 3-dimensional. Instead of up and down, they went around, like a jump rope rather than a guitar string. But there's a second way. What if I hold here and spin? The net effect is as it spins around, well, remember, one of these orbitals, they rise first and fall. We call one of these positive and one of these negative. As you spin them around, that positive is going to be everything on the inside, and that negative is going to be everything on the outside. So one spin would be positive, and one of these spins would be negative. Clearing this up a little bit. The net effect is you create a spherical shape, but it's really 2 nested spheres. So a ball inside another ball. If you put a balloon in another balloon and blow them both up, but you make the inside one smaller. The net effect is that one of these is positive and one of these is negative. And when you draw the wave, it doesn't actually matter which is positive or negative. You can draw a wave like this, or you can draw a wave like this. It just matters that one side is opposite the other. This is a sphere that has one node. This is what we call a radial node. Radial nodes say that, hey, at some radius, some distance, you go to 0. So just hold your arm out and turn around, point it up, point it down, spin it behind you. Everything at that distance is an edge. There's no physical existence, it's just a distance. But at that edge, you have to change phase. Your wave is rising in one spot, falling in the other. They are opposite of each other. Radial nodes show up anytime you need extra nodes and you need a shape that doesn't have any planes. So a 2s will look like this, where a 1s, as we saw earlier, is just going to be one phase. N tells us the number of nodes, and we put it in front. We tell you the number. So what is n? If n is 1, you have no nodes. If n is 2, you have one node. If n is 3, you'll have 2 nodes. How we use those nodes will tell us what our shapes are. But that is what n tells us. There's also the value L. L can be anything from 0 up to n minus 1. So when we have a shape that we say, hey, n equals 1, well, there are only so many L values possible. Specifically, L can be 0. Now, that doesn't mean L isn't something. It means it is 0. But if your n is 2, L has options. L can be 0 or L can be 1. The more nodes you have, the more ways you can use those nodes. L is telling us how nodes are used. N was the number of nodes. L is how we use those nodes. Now, what does that mean? Well, if L equals 0, we call that an s orbital. If L equals 1, we call that a p. If L equals 2, we call that a d. L is actually telling us the number of planar nodes. So when I had that 2s, well, n told us it was 1 node, and s told us it was 0 planar. This is how we said, well, that means it has to be radial. I had 1 node total, and it could not be a plane. Well, your only 2 options for nodes in 3 dimension are a flat plane or a radius. So any nodes that aren't planar must be radial. If instead we were told it's a 2p, p tells us one of them must be planar. I only have 1 node. So I know it's 1 node, and I know that it's 1 planar. Well, that's all of my available nodes. So have a sphere, hack it with a plane, which means that really becomes 2 lobes. One of them is positive, one of them is negative. Anytime you pass through a node, you have to change phase. This is where our p orbitals come from. P orbitals are just when you use 1 planar node. That is what the p orbital means, that you are using 1 planar node. D orbitals are when you are using 2 planar nodes. A 2p orbital looks like this. It has 1 node and that is a planar node. It says, hey, everything along this flat surface has to be 0. I can't have any wave there. I can have wave after it, and there's a big sphere on either side, but it's 0 in the center. Thing is, these are just shapes. When I have an electron and it goes on a nucleus, it takes any shape it can. It wants to take the lowest energy shape. That's the most stable. Higher energies can fall down, but lower energies can't fall up. Something has to push them up. So you try to take the lowest energy shape you can, the least nodes and the least energetic node. So these quantum numbers just tell us how many nodes there are. Well, there is another set of quantum numbers. This is the m sub L. These are the magnetic quantum numbers. So we've had our primary, we had our secondary, now we have our magnetic. These can be negative L through positive L. So for any given combination, once you pick something like 2p, here's my p orbital. To have a p orbital, there are actually 3 combinations. Because L equals 1 for this shape, this comes with 3 varieties. When L is 1, you can have m sub L be minus 1, or 0, or plus 1. That just means it has 3 options. The number itself doesn't mean anything other than being different. What are these 3 options? Well, direction. I put my plane vertical. What if I'd put it horizontal? I could have had the plus and minus below. What if I put it in the plane of the board? One would be coming at us, and we couldn't see the other side. It'd be on the opposite side away from us. So if we try to draw that, 1 plus and 1 minus. There were 3 planes. The vertical, the horizontal, and the perpendicular, the one coming straight at us. M sub L just tells us how many different ways I could have put those planes together. M sub L tells me how many ways I could have used that planar node. Because each of those are a shape an electron can take. If I have a second electron come in, if I have an electron come in and it takes this shape, well, another electron could take this shape. And they could just be existing right next to each other. They don't overlap with each other. They don't interfere. They both reach 0 at the same point. They're not doing anything to each other. Their waves are neither constructively nor destructively interfering. If that's the case, they can coexist. So this is what m sub L lets us notice. It lets us see that, hey, I could have had multiple possible waves of the same shape just going off at different angles. A little hard to draw the in and out one here in pink. But that's what m sub L is telling us. There's 0 reason you can't have an up and down p orbital and a left and right p orbital both exist. They're both a shape an electron can take, and they don't interfere with each other. And so you actually have a lot of shapes electrons can take, which is good because some elements have a lot of electrons. Now, we don't usually indicate the m sub L for most of our purposes. You might see a px, py, pz to describe a p orbital sometimes, but for this course, we're not going to be differentiating between them. But m sub L does let us explain why we have multiple p orbitals. Because if we actually try to start applying these towards the periodic table, well, if I have 1s, this is my lowest energy. It has no nodes. The less nodes you have, the longer your wavelength, the lower your energy. my electrons can fit, and the truth is, we draw electrons as these half arrows, you can actually fit 2 electrons per orbital. There's one more difference between them. One can be what we call spin up, one could be spin down. They're not physically spinning. The name is from before we knew what was going on, and they just called it spin. It has nothing to do with spinning around physically. But the idea is, as long as they're different, those electrons are slightly different in their existence, and so they're not trying to be exactly the same, so they're not interfering with each other. You can get 2 electrons per orbital, and that's it. So if you have an atom, and you've put 2 electrons on, and a third electron tries to go on, well, what shape is it going to take? It has to take a stable shape around the nucleus, and it cannot take the lowest energy. That's already been taken. Imagine if you have kind of a cliff and a valley, and somebody up here is throwing rocks down. Those rocks will pile on the bottom, but eventually the bottom's full and they have to pile on top, and then they pile on top. Later rocks and later electrons have to go to higher energies. The bottom ones are taken. Well, all of the shapes that have 0 nodes, that's only 1s. I can't have a P, that would require a node. I can't have a D, that would require 2 nodes. So that's it. N equals 1, there's just one shape. But I can bump it up. I can make N equals 2. Well, now I have options. I can have no planar nodes, which gives me an S, or I can have 1 planar node, which gives me P. And there are 3 ways of doing that. The left-right P, the up-down P, and the in and out P. The net effect is the shapes that this describes. When you have 1 node, there are 4 shapes possible. A sphere with a radial node, or 3 different double lobes with a planar node. These are all the shapes that have 1 node, and that is all N is telling us. It's just saying, hey, what are all the shapes that have 1 node? All of the N equals 2s. That is what it is telling us. These are the possible shapes that have 1 node. A radial node is less energy than a planar node, and so the S is actually a little bit lower. If you imagine this as energy, S is lower than P, because radial is less energetic than a planar. And so the third electron will just pop right there. It goes to the next lowest possible. A 4th electron, well, you can pair. A 5th electron, well, now the bottom ones are full, so it has to go to the next lowest. That's the 2p. A 6th electron, a 7th electron, an 8th, a 9th, a 10th. They will spread out in equivalent orbitals first before they pair. So we saw 5, 6, and 7 spread out, and then 8, 9, and 10 pair up. So up to the first 10 electrons that we put on atoms, we now know the shapes those electrons will take. What are their orbitals? Which ones are higher in energy, which ones are lower? That is what quantum numbers is telling us.